We are live. What is that? Mic check. Music check. Screen check. Good. Okay. Oh, I haven't fixed this. Let me just quickly fix this. Minimum 0, maximum 10, increment 1, save. Okay. My apologies. Now, we're going to look at the exponential curve, and I try and relate every curve to stuff that we've done before. So I kind of always relate it to the straight line. Now, we call the straight line y equals mx plus c. I'm going to call it y equals ax, kind of like, that a that we were using for everything else, like ax squared, x cubed, blah, blah, blah. So I'm just going to use a just for a bit of consistency. So a times x, what does that do? Well, depending on what your a value is, it's just the same number times by another number, but this same number is called, well, it's called a scalar, but we sometimes call it a constant, which just means that this whole graph, or the output, is just going up at a constant rate. So a constant rate just means at the same rate, so just like a straight line. So that's kind of what happens when you've got a straight line. You've got ax, it's being times by a constant, going up by a constant rate, straight line. Now we're going to look at a different type of graph, which instead of going up at a constant rate, it's actually going to go up at an exponential rate. And you can think of the word exponential in terms of like real life. Wherever you heard the word exponential before, well, you might have heard it kind of everywhere, I guess. Like the moment the COVID case numbers are going up exponentially, that might be something you hear in just like general conversation. And it just means that instead of going up at a constant rate, so you don't say that COVID numbers are going up at a constant rate, not going up by 20 every single day, and now it's at like 800. That's not how it's worked. It's gone to 20, 50, and then it went to 200, and now it's at 800. Like, it's gone up really, really fast, and that's what exponential is. So rather than being a times x, it's actually going to be a to the power of x. Now, as you'd imagine, if I had a to the power of x, the second you start increasing this number quite significantly, so if I put a squared there, let's actually put some numbers in. Let's say this was a 2. When I put a squared there, that's 4. When I put a cubed there, that's 8. When I put a 4 there, that's 16. You can see the numbers aren't going up at a constant rate, just like this would have. So if this was a times x, this would be 2 times 2, or 2 times 3, and that's like 4 and 6 and 8. And it's going up at the same constant rate of plus 2 plus 2. This is going up by, this is being added 4 and then added 8. Like, the numbers are getting massive quickly. That's what an exponential is. So we've got the graph y equals, now it's some number, a, to the power of x. That number doesn't really change much. So if you look at the graph on the top left, I mean, if it's 1, then 1 to the power of anything is just 1, so that's why it looks like a straight line. But when we increase this by 1, so I've got a to the, so y equals 2 to the power of x, you can see that it just increases significantly. So they were the points that I was talking about. So you can see if I go over to 1, so if I put a 1 into my equation, so 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. So you can see it just goes up heaps fast, really quickly. Now, if I increase this again, what do you reckon is going to happen if that was a 3? Well, that's going to be 3 squared, which is 9. 3 to the power of 3, which is 27. So it's going to go up faster. So you can see the more that I increase this number here, it's the same graph. It just goes up really, really fast. And you might notice that there's something that doesn't change on the graph. It's this 1 value here. And it's kind of, I guess you can kind of ask yourself, why is 1 the y-intercept every single time? And there's a reason for that. And I'll show you. I'm just going to use like the bare minimum y equals a to the power of x. If I want to find the y-intercept, I make what, x equals 0. So then if I do that, y equals a to the power of 0. Anything to the power of 0 is what? Well, it's actually 1. That means no matter what my a value is, my y-intercept is always going to be equal to 1. Yes, so I guess that's the only argument I need to make there. So let me just draw my graph. My exponential kind of looks like that. So it always cuts at 1. That's my y-axis, that's my x-axis. This is y equals a to the power of x. Now I want you to consider a couple of things. The first one's going to be, what happens if I multiply all of this by something? So if I put like a 2 there or something, what's going to happen? That's actually beyond what we're looking at already, but pretty much it's just going to scale it, so it's just going to go up, and the y-intercept would actually change again. what would happen if I put a minus here? What would happen if I put a minus here? So these are kind of the things that we need to think about. And before I do any of that, I'm just going to, I guess, list a couple of the things that you might, I guess, notice just by kind of looking at the graph. So the first one, and I'm going to use the notation I was using before. Now, as x approaches infinity. Now, what does that mean? That just means as I go across the graph towards this direction, in the x direction, as it gets really, really big, what happens to the graph? Well, it's going really, really high. So that means my y value also approaches infinity. So that means as x approaches infinity, y also approaches infinity. Now, conversely, the backwards, as x approaches negative infinity, what happens? Well, as x goes this direction, what's happening to my y value? Well, it looks like it's going really, really close to 0. So if you just look at the graph up here, you see that it never actually touches 0. It looks like it does, but if you kind of zoom in, it doesn't ever. There's also a reason for that. And I like bringing in, this is kind of bringing like our exponential and logarithm kind of topic and showing you graphically what all of the stuff that we looked at meant. Okay, so as x approaches negative infinity, y approaches 0. And the way that you can kind of argue this is if I just put some really small, so maybe negative infinity, if I put a really small value in here, and I would actually just do this in my calculator, if I went 2 to the power of, I like just putting negative 99. If you do that, oh, negative 999. If you put negative 2 to the power, 2 to the power of negative 9999, your calculator can only, I guess, round so much. And so, you can see that, but it says it's equal to 0. There's another reason for, do I want to go? How long is this video? Yeah, screw it. Think about this. So let's go example. 2 to the power of negative 999. What is that the same as? Well, when I've got a negative power, isn't that the same as 2 to the power of 999 to the power of minus 1? Which is the same as 1 over 2 to the power of 999. And if you have a denominator of a fraction that is massive, you might as well just call it 0. So that's just equal to, well, I can't really say that, it's approximately equal to 0. Is there anything else I really want to talk about? Not really. Okay, let's start graphing some. So let's go with 1, y equals, I don't know, 2 to the, let's do 3. Y to the power of x, y equals minus 4 to the power of x, and y equals 3 to the power of minus x. So I guess you've just got to be able to identify each of these and be like, what do they kind of look like? So I'm going to draw some axes. I'm going to omit the x and y. Screw it, maybe I'll write them. Y, x, y, x. Okay. I just want to figure out, this is as far as we go. Obviously, you can go further, but this is kind of all we need to be able to graph at this stage. Now, 2 to the power of x, that just looks like my standard curve. Cuts at 1, and that's it. But again, kind of like the other looking at hyperbolas and stuff, I have no sense of scale, so it's good to just put in a point. Generally, just chuck in x equals 1. So when I put a 1 in here, that's going to be, so let's just go y equals 2 to the power of x, y equals 2 to the power of 1. That means that equals 2. So that means that's a 0.1, 2. So all I did was put a 1 in there, and then I found out what y equaled. So that helped me find a point, and that can tell me kind of like the scale. Now, I want you to think about what happens when you put a minus in front of your exponential. It's the same thing as what happens when you put a minus in front of anything else. So if I had y equals minus x squared, what did that do to the original graph? Well, it flipped it upside down. So exactly the same thing here. It's just going to be like this, but upside down, so like that. And you could probably guess what this value here is going to be. Well, it's just going to be my normal y-intercept, but flipped upside down. So that's going to be minus 1. And again, you can just use a point here for scale. I always just use x equals 1. When I put a 1 in there, I'm going to have minus 4 to the power of 1, which is just minus 4. So that there is going to be minus 4. And last thing, what happens when the minus is right next to the x? Well, I guess you can think of it like, let me show you on the right, yeah. I can't really think of a way of explaining it. I just guess each of your outputs are just kind of going to be backwards. Like, can't really think of a way of explaining it. I guess you could rewrite this as 1 over 3 to the power of x. And that would mean that instead of going up really, really fast, it's actually, because this number is getting bigger, it's actually getting smaller. So it's actually going down and starting big. That's one way of thinking about it, but really all it does is it flips it the other way. So when you've got a minus out the front of the whole thing, it flips it this way. If you've got a minus just next to the x, it flips it this way. But I guess the way, if you want to think a little bit more deeply about it, it turns it into a fraction. And if I had a minus x value, I'm putting a minus in here, this is going to cancel out, so minus, minus, and I have a really big number. So the graph actually starts off really big and then goes small. So in other words, it just looks like this. It's got the same y-intercept. I can put another point in here for reference. Maybe I'll put -1. When I put a -1 into here, I'm going to have minus minus 1, which is going to be 3 to the power of minus minus 1, which is the same as 3 to the power of 1, which is just 3. So at that point, there's 3. But that's all you really need to be able to do. If I were to give you a challenge problem, we can, again, just move these things left and right. And there's a couple of things I want to talk about with this challenge problem. I'm going to make it y equals 5 to the power of, in brackets, x minus 2. So just think about that's going to move it left and right. What happens when I then add a value on the end? That's going to move it up or down. Now, I want the x-intercept here. I'll make this a minus so that it has an x-intercept. Now, the y-intercept, I want you to think about what's going to happen when I try and solve for this. So if I try to find a y-intercept, I'm going to make this, oh no, sorry, if I want to find an x-intercept, I need to make this equal 0. Then I need to solve it for x. So in order to do that, I'm going to have to move the 3. I'll have to divide by the 5. No, sorry, not divide by 5. Now I'm going to get rid of this 5 because there's this power on top. And prior to, so pre-year 10, you might have thought this is kind of unsolvable. So maybe I'll give you some steps. Here you make it this, minus 3. Then you've got 3 equals 5 to the power of x minus 2. So then you've got to think about how am I going to get this 5 out of there. And I really like this stuff because it brings, I guess, to life because we've solved these this year. It kind of brings to life why we were doing this in the first place. Well, we want to be able to find x-intercept. We want to be able to draw these things and what they look like. And you might think, why the hell would I want to draw an exponential? Well, exponentials are kind of common in real life, and there's a lot of real life applications, especially next year, that we'll see. We won't see them this year, really. We'll see them next year where you're given word problems, and they do end up, a lot of the time, becoming exponentials. Things like population and like rates of change and I can't think of anything else, but essentially you're going to see it quite often. I didn't mean for this video to be 13 minutes, but I ramble because I am pretty passionate about this stuff. Like, I do like this stuff. I think it's good to see that this stuff that we're doing with logarithms and exponentials and solving log equations and stuff actually has some meaning. And I think that's really important to be able to see. Anyway, I'll stop there and I'll leave you with that. I'll leave that line of working out. But essentially, if you don't want to do any of that, you just need to be able to graph these. Just need to realize the minus is going to flip it this way, minus up here is going to flip it that way, and this number really doesn't change anything other than how steeply it goes up. That's all you really need to know from today. And that'll be it.